Welcome to qnawire.
Okay, so this is problem number 6 of chapter 23. In this problem, we are given the slit separation, d equal to 4 centimeters. We are also given the wavelength, which is lambda, equal to 1 centimeter. And the distance between the slit and the screen, capital L, equal to 7 centimeters. We are asked to draw the double slit with 6 crests coming from each of the slits. So here, even though I drew the crests of different colors, they are from the same wavelength. They are of the same wavelength coming from the same source. The wavelength is 1 centimeter, so the distance between the concentric circles here of these blue crests it's going to be 1. Same thing with the red one. The concentric circles are separated by a wavelength, so 1 centimeter between each crest. They are diffracting from the upper slit here in red, from the lower slit in blue. And what we're going to draw first is constructive interference occurs when a crest from the top slit crosses with a crest from the bottom slit. So this would be constructive interference at this intersection point. Notice that these intersection points form a line all the way to the screen, and that's going to be your zero order bright fringe. Okay, so from the center of the slit here, we're going to align those points, and that's going to be our zero order bright fringe at this point on the screen, a distance L from the double slit. For your first bright fringe, again, we're looking for that point of intersection between the bottom crest and the top crest, and they occur here. You can see these intersections here along this line. So if we connect those dots from the center of the slit, it's going to be approximately right here. Okay, so now we are going to draw a rectangle on the side here to try to get this as a approximate measurement here. This height of the rectangle is going to be approximately that distance from the zero order bright fringe to the first bright fringe. So now let me make sure I don't resize this. What I'm going to do, I'm just going to rotate it, and then I'm going to align it with the opening here of the bottom slit, because remember, each wave crest is approximately, it is 1 centimeter here in this graphical representation. So notice that that distance from the 0th bright fringe to the first bright fringe is, from the looks of it, it's just shy of 2 centimeters. Just shy of 2 centimeters. So approximately, like, let's say 1.9. So we're going to say Y1 experimental is going to be approximately 1.9 centimeters. So how would this compare to the theoretical value of Y1? Well, how can Y1 be calculated theoretically? For the double slit experiment, we assume that the screen is much further than the openings of the slit. So in this case, notice that it's only 7 centimeters away, whereas the distance between the openings is only 4 centimeters. So even though small angle approximations wouldn't work here, let's still use the small angle approximations just to get a theoretical value and to compare against this experimental 1.9 centimeters between the zero order bright fringe and the first bright fringe here. So if we assume small angle approximations, we have sine of theta. Sine of theta m is going to be approximately tangent of theta m. Okay, this is valid for small angles. Now, like I said, even though that's not the case here, we're just going to proceed just to get an experimental value. So sine of theta m, recall that the expression from the double slit experiment is that d sine of theta m is equal to m lambda. And then here we can solve for sine of theta m as m lambda over d. Okay. From this picture, though, we can see that tangent of theta m is going to be equal to opposite, which is y at m, over adjacent, which is L. So for small angle approximations, we can set these quantities equal to one another. So let's go ahead and do that. On the left-hand side, we have sine, which can be expressed like this. And this is going to be approximately equal to tangent of theta m, which is this. So here, let's solve for y sub m. Okay, let's use this equation to get a theoretical value for y1. So let's call this y1 theoretical. It's going to be m times lambda, so m is just going to be 1 for the first bright fringe. Lambda is going to be 1 centimeter. L is going to be 7 centimeters. And the slit separation is going to be 4 centimeters. Okay, let's see what we get. 7 divided by 4, we get approximately 1.75. centimeters. So this is going to be our theoretical estimation. Notice that this is very close to our experimental value, just shy of 2 centimeters. So let's see what that percent difference is. All right, so let's recall that percent error formula. So percent error formula tells us that we're going to compare the absolute value of the theoretical value minus the experimental value over the theoretical value. Okay, so we're going to use this formula. All right, so the theoretical value, we have 1.75 centimeters. The experimental value is 1.9. And we're going to divide that by the theoretical value, which is 1.75 centimeters. Centimeters here. So those are going to cancel. And to get a percentage, let's not forget to multiply by 100. So this is all going to be multiplied by 100 so that our answer is going to be a percent. So let's go ahead and run that through the calculator. Let's see what we get. Okay, and 8.6% error. Okay, so this theoretical approximation is not that bad, and then it agrees it's less than 10% what we observe here. So the difference between the two is less than 10% of the theoretical value for the first bright fringe. Okay, this concludes problem number 6.